Okay, so I'm going to introduce Ken. Ken has come to visit us for several months on a mini sabbatical or a real sabbatical. I'm not sure what it is. But...
Real
okay,
sabbatical.
So Ken got his PhD from Harvard a few years ago. And he says back when they were still using tape recorders. So I think he's going to talk about the tape recorder. And many of you in the audience don't know what a tape recorder is anymore, but old people like me do. So he came to NCAR as an ASP postdoc. Worked with Giebreser and Sasha, among other people. And then he went and joined the physics department. Now he's a professor of physics at New Mexico Tech in Socorro, New Mexico. He does research in spectroscopy and radiative transfer, remote sensing, climate dynamics, feedbacks, and he says whatever looks interesting. And he tells me he's an expert in fantasy football, so he'd like to challenge. He can also play ping pong, so he fits right into being an ACOM.
Do we have a league, a fantasy football league at NCAR?
Not yet.
Not yet, okay.
What is fantasy football?
Okay, that's a topic for the next seminar. That's right.
Anyway, and you're here visiting till November?
To the end of November.
Yeah.
Yes.
So welcome, and we're going to hear about those topics.
Thanks, Bill. Thanks very much. Yeah. So this is something that I've been working on for a long, long time, and it's before I got the paper in any shape to submit, another 3 or 4 years had passed, and so it was great. The record was longer, and so there was more stuff to look at. But I think it's now to the point where I can at least talk about it. For those of you that don't know about New Mexico Tech, and that's probably most of you in the room because it's a very small school. It's in Socorro, New Mexico. We have about 2,000 students. The physics department has about 100 students, undergraduate students, and we have about 30 grad students, both masters and PhD students. About half of them are doing astrophysics, working primarily with data from the Very Large Array radio telescope. And the other half of the department does atmospheric physics, and I'm a part of that. And the co-authors are Jonathan Zhang and Hui Su at JPL. So let's see if this is, there we go, okay. So what's this guy doing in Boulder? Some of you know why I'm here. Many of you probably don't know that I'm here to do mostly hiking with my dog in the wilderness area. But actually, I thought I would just give a quick rundown about why I'm here, because you might see me in the halls, you might wonder what the heck I'm doing. I want to work with the frappe data. I'd like to understand the contributions of the oil and gas activity to emissions of methane and other hydrocarbons. And there's an obvious connection to the San Juan Basin and the Four Corners area. So that's an area of interest of mine. Oops, went the wrong way. I want to look at mesosphere and lower thermosphere nitric oxide while I'm here in Wacom. Here's a spectrum that I'm showing, because I have to show a spectrum in every talk that I give. And this is a spectrum from RAIDS, which was an experiment on the International Space Station a few years ago. We have about a year of data. One of the things that you can do with this black area, here's a limb spectrum in the middle UV, and the red is kind of an estimate of the Rayleigh solar scattered. So if you take the difference, you get these peaks here, which are observed emission from magnesium, ionized magnesium, and there's some oxygen, there's some O2 VK bands, and then the nitric oxide. So we can retrieve nitric oxide, and I want to look at diurnal variability in the lower thermosphere from Wacom and compare to the observations. And then finally, well, maybe not finally, because I think I've also probably got about 2 or 3 other projects that I want to work on while I'm here. This is stratospheric loss in global lifetimes of CFC11. This was a SPARC report from 2013. I contributed it on a chapter with Elliot Atlas, I just saw here a few weeks ago, looking at a reevaluation of the CFC11 lifetime. But one of the limitations of the method that we were using was that the data from MIPOS was not, the vertical resolution wasn't that great for being able to calculate the CFC11 loss. And hurdles has much better vertical resolution. So I want to use the hurdles data to reevaluate the CFC 11 lifetime. So that's kind of what I'm doing here. But I don't have any results yet on any of this stuff to talk about. So I'm going to talk about the tape recorder. And the motivation is that I'm interested in understanding the ascending branch of the Brewer-Dobson circulation. Most of you in here probably are experts on this topic, so I don't need to go over it, but you know, this has been around a while from Brewer and Dobson, this kind of mean circulation in the stratosphere where you have upward motion in the tropical lower stratosphere and downward motion at high latitudes. And this area here is obviously one of great interest these days, and one of the problems, though, is that the rate of upwelling is very slow. It's like tens of meters per day, maybe a kilometer a month. And it's very difficult to measure. Now, there are some measurements out there using VHF wind profilers. The problem is that they're in spot locations, and you're not getting the tropical mean. And there may be preferential areas for ascent in the tropics, and the measurements that we have, or at least that I've seen in the literature, there's large uncertainties, and the magnitudes that they get are quite a bit larger than what we would calculate based on thermodynamic balance. There's little data for validating these vertical motions that are simulated by the models or in the reanalysis systems, and I'm showing an example here from a recent paper that was submitted by Jonathan Zhang et al., and it shows kind of vertical velocities that you can calculate from the Aura MLS data in a manner that's somewhat similar to the way I'm going to describe. And then it compares it with the vertical velocities that you get from MIRA, MIRA2, and ECMWF, among others. And particularly, these three reanalyses have considerable discrepancies between what you would get for the vertical velocity based on their water vapor tape recorder data and the Aura MLS tape recorder. Okay. I don't think it necessarily means that the vertical velocities in the reanalyses are wrong, but if you calculate the vertical velocity using their water vapor in the same way that you do using the water vapor data from Aura, then you get these big discrepancies. Okay, so now here's why it matters, and here's a methane plot for Sasha here. It matters because the overall chemical composition of the stratosphere is impacted by this Brewer-Dobson circulation. It controls the distribution of ozone and other greenhouse gases. And what I'm showing here is a plot of the methane radiative forcing, which is the net long wave flux change at the tropopause, calculated as a difference between 92 and 1750. It's the way we used to calculate radiative forcing back in the 90s. But instead of using a global average, it's separated by latitude and month, because the net flux change at the tropopause is very sensitive to how much methane is above you, and the methane decreases quite rapidly above the tropopause. And so even though the global mean radiative forcing from methane at this time in 92 was about 0.55 watts per square meter, you can see a very large latitudinal variation in the radiative forcing, and a lot of that is due to the stratospheric distribution of methane, which is controlled in a large part by the influence of photochemistry, photochemical destruction, and that circulation. So that's why it matters. Now, okay, so this is back in the day, back when I was a grad student, we had, instead of iPods, we had Walkmans, which was a little cassette tape. And the tape would flow this way. We'd have an erase head, a record head, and a playback head. Okay, well, in analogy to this tape recorder, we're going to look at water vapor data where the tape head will be near the tropopause, and then we're going to see this signal propagate upward. Okay, and this This phenomena was actually first introduced by Phil Mote using halo data from UARs. And what they looked at, we'll look at the bottom plot first. The bottom plot shows mean water plus methane from halo as a function of month of year and as a function of height. The tropical tropopause is right around here at 16 kilometers or so. And what they saw were these series of wet and dry signals that would propagate upward in the lower stratosphere. And these wet and dry signals were correlated very well with the mean tropopause temperature in the tropics. So it was discussed in that paper that the tape head is located at the tropical tropopause, and the recording mechanism for water vapor, at least, is the seasonal variation in temperature. For the most part, I know there's a lot of processes that control water vapor in the tropical lower stratosphere, and it's not just temperature. You can have overshooting convection, you can have freeze drying, you have all kinds of microphysical processes. But to first order, you could say when it's very cold, you get dry air entering the stratosphere. When it's very wet, or when the tropical tropopause is warmer, then you get moisture air. And by the time this happens, the dry patch has ascended upward, and that's the tape recorder. And the tape speed then is related to the vertical velocity of air parcels. It's not exactly the vertical velocity, so you have to keep that in mind. Okay. Oh, by the way, if there are questions, is it customary to ask them during the talk, or we usually wait to the end?
Typically at the end,
Typically,
because we should answer questions into the mic.
Okay. Because I was going to encourage people, if there's something that's not clear, just, shout out or something. So what we've done is used water vapor and carbon monoxide from MLS. This gives you the details of the data. Tropical means, so we're using plus or minus 15 degrees latitude, and you can play around with that a little bit. You can get a cleaner signal if you narrow in on the tropics. However, it gets noisier, there's less data to work with, but you can avoid kind of the fringe subtropical effects at certain times of the year. But anyway, the plus or minus 15 is what we kind of stuck with. These are the vertical resolutions for water, and it's 3 kilometers roughly for water, 5 kilometers for CO. And that has kind of an influence on the temporal resolution you can get. The vertical resolution relates to the temporal resolution. Okay, so here's what the tape recorders look like from MLS. The top one is water, and the bottom one is CO, and we go from 2004 to the end of 2014. And so the yellow areas are where the anomaly is moist, and the blue areas is where it's dry. And similarly for CO, this is high CO, low CO, as a function of pressure. So we're going from from 100 to 10 millibars or hectopascal, and the tropopause, the tape head, is right about here. And you can kind of see that things are going up pretty fast initially, right above the tropopause, and then they slow down for a while, and then they speed up again. And we're going to see that in the vertical profile of vertical velocity. The water signal persists for quite some time. You can track it almost all the way up to 10 hectopascal. The CO signal is much noisier. It seems to, at least to my eye, it seems to go away a little bit faster. It doesn't persist as high into the stratosphere. The maxima don't occur at the same time as the water, and in fact the processes that govern the tape head business here for CO are quite a bit different than they are for water. It's not the seasonal variation in temperature primarily, but it's a seasonal variation in convection and surface emissions coupled together. Because you've got to have both to pump the CO that's emitted from the surface into the TTL, the tropical tropopause layer, where it can then make it into the stratosphere. And it's also kind of interesting that you see it's not like a well-defined maximum and a minimum, but you get these, at least in terms of the maxima for CO, you get these periodic pulses that last a month or two, and then they kind of go away. So it's not as, and we'll see that in a minute from the curves that I'm going to show. What I'm going to show next are slices through here. So 2 slices for water, 2 slices for CO. The other thing to notice from this is that the vertical levels for CO are spaced farther apart than they are for water, and that's just the nature of the retrieval for MLFs. So they retrieve water on a much finer vertical grid than for CO, and that also has implications for the velocity that you can derive. So here's what the slices look like. So here's the 68 hectopascal slice for water and the 56.2 for water. Here's the 68 for CO, so same pressure. And you can, again, you see these maxima are kind of punctuated with these peaks, and I think that has to do with the way convection operates, where you get these kind of groups of convection that periodically give you a maximum in CO. But again, I'm kind of well, I don't know if that's not been demonstrated yet. But anyway, but the data are quite a bit noisier for CO, and these are artifacts that this is from an earlier version of the data set, and we've gotten rid of that, but still. Okay, so what we do is we look at the phase lag between adjacent levels to get omega, which is dp/dt. And this has been done before by others. Noano and Schoberl did it in 2008. Thomas Fleury did it most recently. It wasn't always clear to me in those papers how they did it. They always just said, well, we're going to correlate the phase lag between levels and get the velocity. But the devil's in the details here. So I pretty much just kind of came up with my own method. And it seems to work. And I'll describe it here. But here's here's an example. For example, like this minimum here, and you track it up here. So this might be kind of the slope of the phase line. Whereas here, and I don't know if you can see, it was clear on the computer, but from my perspective, those lines look like they have the same slope. But maybe you can see that this one has a steeper slope than this one. So the velocities are changing with time. You can actually see it by eye here in the data. So here's how it works. You take a day on the lower level, and here's the same day on the upper level, and you correlate a 1-year chunk from here with a 1-year chunk from up here. Okay, then you move to the next day up here, and you do the same thing. You keep this one fixed, but you correlate it with a 1-year chunk from the next day, and the next day, and the next day. And you go through, and you step through till you go through about 100 days, and you find a maximum in the correlation. Okay, so you take these 1-year windows. Why 1 year? Well, that's approximately what you need to capture these big features here. But instead of using a boxcar, which I think is what was used before, I use a Hahn window, which is a window that's used a lot in spectral signal analysis. It allows you to weight the data near the center of your window more than near the edges. And I think it gives us a little better time resolution. So let's see, is that all I want to say about that? Okay, so now you get a number you find a maximum in the phase lag, so you get phi. So you can calculate omega, which is just delta P, the difference between these two pressure levels, divided by the phase lag, where you have the maximum in the correlation. But what is that really telling you? I mean, where is that velocity? Well, the best you can do is say, okay, I'm going to assume that that's the velocity halfway in between, log pressure. But what about time-wise? Well, the best you can do then is just take the mean between these 2 days and put it right there. So that's your estimate of the velocity. But you can kind of see that's going to run into problems, because if I move to the next day and the phase lag is a little shorter, now I'm going to get another estimate of the velocity, but it'll be for the day before, right? Because the mean is going to be a little different. So you have to be careful how you string together all of these means, and you can get multiple values for one day and all kinds of stuff. So there's some signal processing that has to go in to give you a nice smooth velocity time series. But oh, this is just an example, and this is just now to convince you that the slopes really are different between these 2 points. So for this day, this is what the correlation coefficient looks like as a function of lag between the 2 levels. And the correlation max is around 90 days here. So it's about 90 days for this minimum to propagate up to here. Whereas over here for this day, if you plot the correlation coefficient versus lag as you go through the upper signal, the maximum in the correlation is about 52 days. And so the inferred vertical velocity is much faster for this day than it is for that day. Now, these are typical kind of plots of what the correlation coefficient versus lag looks like. Some of them, though, aren't quite so clear-cut as this. Or even, this one you could say, okay, well, there's some uncertainty here because it kind of flattens out. And some of them look really flat. And so you get a large uncertainty in your vertical velocity. And you just have to live with it. There are a lot of details. As I mentioned, the devil is in the details here, but hopefully you get the picture. So in the limit of no diffusive or eddy mixing, this derived ascent rate is a measure of what's termed in the literature W star bar, which is the vertical component of the residual mean meridional circulation. Okay. This is the thermodynamic equation that relates the temperature tendency. This is the horizontal advection. This is the vertical advection, which is related to this vertical velocity, and Q bar is the radiative heating rate. And there's been a lot of work on the magnitudes of these terms here. And in the tropical lower stratosphere, this term and this term are both pretty small compared to these two guys. So in a kind of first order balance, you have this upward motion being balanced by the radiative heating. In other words, you have radiative heating, you have air moving up, adiabatic expansion, it cools. So the cooling effect of this upward motion is balanced from the heating effect of the net radiative heating. It's not only solar, but it's long wave as well. And so what we've done is calculated Q bar using a long wave and short wave radiative code, and used measurements of the vertical gradient of temperature to estimate the upwelling from radiative balance and compare it with the upwelling from the tape recorder. And if we do that, well, let's see. Okay, so here's a plot. If I take the mean of all of the time series of vertical velocities and just plot that versus altitude, this is what I get. The solid line is from the MLS water tape recorder. Let's see, it comes up here and it goes like that. The dashed line is from the CO tape recorder. And you can see pretty good agreement here. But in the lower stratosphere, the CO tape recorder velocities are much faster. And I don't quite understand why. I think it's just related to the fact that the CO signal is much noisier, and so there's a lot more uncertainty there. I'm not sure. I think what's happening up here also is that the CO tape recorder signal just peters out, and so you're pretty much losing signal there. But anyway, so you get this kind of minimum in vertical velocities here, And the other thing that I should point out, and Schoberl did this too, was that the velocity you get from these kinds of calculations is really an upper limit to the velocity. Because you can imagine if there's vertical mixing, the vertical mixing is going to tend to wipe out these gradients. And if the gradient gets wiped out and these anomalies go vertical, then you get an infinite velocity, right? So mixing will always tend to give you an effective velocity that's higher than the true residual mean. So the residual mean that you calculate from this is always an upper limit. And so it's amazing to me that this is really slow, and yet it's an upper limit. So it could be even slower than this. But this is the GeoCCM, which is really in very good agreement. The radiative model, when we calculate velocities using the radiative model, we get similar values, but there's this deviation up here that I'm not real happy with. I think it is related to the ozone that we're using in the radiative calculations. Presumably we're using MLS ozone, but I'm still worried that this is a rather large discrepancy that I'm not happy with at this point. But
so the GeoCCM, is that the tape recorder velocity from the GeoCCM or the omega?
That's the omega from the Geos. Yep. That's not the tape recorder. Yeah. I think. I sounded authoritative when I said that, but now I'm starting to think, oh, I don't know. But I don't think they did the same analysis on the Geos. In fact, I don't even know if that generates a reliable tape recorder signal, or if it did at that time.
Probably would.
Yeah. Well, certainly the reanalyses do, because Jonathan looked at them, and you can see them in the reanalyses, but the speeds you get are way off. So this is a comparison now of the time series of the omega star bar at 51 hectopascal and at 42.1 hectopascal. These are kind of goofy pressure levels because, remember, they're in between the MLS retrievals. The black line is what we calculate here and here. The blue dots are daily mean values from the radiative heating rate calculation. Okay? So, and consistent with the previous figure, at least I think this one's at around 20 kilometers and this is around 22. So we're kind of looking at these levels here, here, and here. So in terms of magnitude, they tend to agree, and the time variation also tends to track pretty well at both levels. The radiative velocities show shorter term variations that are not captured in the tape recorder velocity. The tape recorder velocity is smeared out. I think from these plots you can deduce that the effective temporal resolution is on the order of 3 to 4 months, which is about the width of this Hahn window up here. Even though the full width is 1 year, I think you can get a resolution that's better than that using the Hahn window. But there is a limitation to kind of the resolution you can get because of these time lags. Okay? You probably can't do much better than 50 days, which is a month and a half, and that's just a limitation because of the separation of the signals that you're looking at. And what I'm showing here in the middle plot is temperature from MLS, because I was interested in what was related to these variations in omega calculated from, or I'm sorry, W star bar from the radiation code, and it turns out that there's a very good anti-correlation between temperature and the velocity calculated from the radiative heating, which is driven primarily then by changes in temperature and not changes in water or ozone or other things, even though those are important. But a large part, 65% of the variance here in the temperature, or I'm sorry, in the velocity here is due to, or is related to, changes in the temperature. And they're anti-correlated. That is, when temperatures are high, the velocities are low. And that's related to the radiative heating rate in the fact that when the air is colder, the radiative heating is larger. The long wave radiative heating is larger, and that drives a larger vertical velocity. Conversely, when the air is warm, the radiative heating goes down. The warmer you get, the closer you get to radiative equilibrium, and then there's no motion at all. Everything's at a standstill. Okay, so I said tau 3 to 4 months. Oh, dominant QBO features. You probably noticed in looking at this that there's boom, boom, and then, and similarly, it's even, I think it's clear up here that there are QBO features in the time series. And so I'll go quickly through this because we have QBO experts in the room. But for those of you that are not familiar with the QBO in the lower stratosphere, tropical stratosphere, it's a variation in zonal wind and temperatures. You have descending westerlies and then easterlies. The westerlies tend to descend a little bit faster than the easterlies. So if you look at, for example, at the edge between white and dark, it's a little steeper than the edge between dark and light, which has a shallower gradient. Okay? And this is all related to the thermal wind balance, and this has been studied for a long time. I'm showing a figure from Plum and Bell of 1982, in fact, that shows kind of this anomalous circulation that can occur when you have westward zonal winds over eastward zonal winds. It gives you this cold patch here. And remember, cold patch gives you enhanced ascent. Now, this isn't the actual Brewer-Dobson circulation, but this is the QBO-driven anomaly in the circulation. And similarly, if you had easterlies here over westerlies, you would get something that goes like this. And I looked at that figure for a long time and said, how can you get downwelling in the tropics? Till I realized that it was an anomaly plot that they were showing. So it wasn't actually a circulation going this way, but it was the anomaly in the circulation. And one of the convincing demonstrations that this actually works was published by Bill in 1999 using UKMO data. He plotted W star, anomalies in W star versus the wind shear. So negative would be easterlies over westerlies, and positive is the westerlies over the easterlies. And there you got it. A good correlation here between the anomalies in the vertical wind and anomalies in the zonal wind shear. So I thought, well, we should be able to do that. So here I've got the time series of W star bar plotted at 51, 38, and 23 hectopascal, going up from about 20 kilometers to about 26, 27 kilometers, I guess. The black is the time series of W star bar from the tape recorder. The green is the tropical zonal wind shear from the Free University of Berlin, which is kind of the authoritative data holding for QBO stuff. And let's see, I'm going to come over to this side, even though I'll be out of the thing, but I've swapped the axes here. Because remember, the negative wind shear corresponds to the larger velocities, and the positive wind shear corresponds to the very low velocities. And so you can see things track pretty well. It's not great. There's still some other things going on here, but when we have this westerly shear, so okay. What about the Randall plots? What do those look like? Whoops. Well, not as good as Bill's plots, but I'm comforted by the fact that at least I got a negative slope. And that the slope increases as you go up in the stratosphere. Although this is kind of an anomaly here, this point here, but in general, we see a larger dependence of the vertical velocity on QBO as you go further up. The slopes generally increase, but the magnitudes are less than what Randall et al. Found in UKMO data. And I'm not sure I understand why. I think it may have to do with the fact that there's other things going on in this data set. You can certainly see some weirdness here. Some funny distributions in the monthly means that are not captured by just the zonal wind shear alone. I should point out that these actually have been deseasonalized. Okay, so there's not an annual cycle going on, and this is how they were deseasonalized, was by if you take the QBO out of that time series by using that linear regression I showed before and plot the residuals, you can then fit them with sinusoids. And so they're fit in blue here. And I allowed both the amplitude and the phases to vary. The amplitudes here are much smaller than the QBO amplitudes. Before we were seeing QBO amplitudes that were, that were like 0.01 centimeter per second, or maybe even 0.02 up here. But the annuals are much, much smaller, like 0.005, or in some cases 0.003. These annual signals might be underestimated, though. As I mentioned, the time resolution of this vertical velocity is on the order of 3 to 4 months. And so you might not be able to capture, particularly if they're not sinusoidal. If the annual variations aren't sinusoidal, you could underestimate the amplitude by fitting them with a sinusoid. When your time resolution is on the order of a significant fraction of the period of your cycle. But one thing that came out that kind of gave me a warm and fuzzy feeling was that the maximum upwelling at all levels occurred in November and December. They don't all line up. These phases differ by a few weeks. But in general, they all seem to occur in November and December, and that's consistent, again, with a paper, Randall, Garcia, and Hu in 2002. I think they were looking at actually more shorter term variations in the upwelling. Some of these pulsing events. What I've plotted here, well, I haven't plotted, this is from the Randall et al. Paper, but it shows temperatures. These are tropical temperatures, and it shows the minimum temperatures occurring during this phase around between November and January. And it's consistent with the eddy heat flux driving. This is the EP flux. The dashed line is from the southern hemisphere. Solid line is from the northern hemisphere. The interesting thing is that the southern hemisphere EP flux kind of lasts further into the season, way into the southern hemisphere spring, and by that time the northern hemisphere picks up. So if you add these together kind of to get the global, you kind of find that it actually peaks here in the November, December, January period. But one of the things I'm interested in are these pulses, these kind of week-to-week pulses. I'm not going to see it in this MLS data, but maybe if we have better vertical resolution, there's a chance that we can get vertical velocities with kind of monthly time scales, as I'll mention here in a minute. Okay, so you can take out the seasonal cycle, you can take out the QBO, and here's what's left. Now, what I did actually was average 3 levels, because it is very noisy, and we're down, way down, almost to the noise limit. 0.003 is even below the annual signal. But these are the kinds of variations that you get if you deseasonalize and deQBO the vertical velocity. There was a significant Enso event here in 2009. So one of the things to look at is Enso. And in fact, the folks here have been looking at Enso for a while on the effect of Enso on the tropical lower stratosphere. And so this is a couple of figures from a paper by Garcia Herrera et al. Showing Enso composites. This is warm minus cold in model temperatures at 10 degrees north. So this is WACOM. This is the middle atmosphere ACOM model, and this is ERA 40. And we're looking at longitude versus altitude, from 0 to 100 kilometers. But what we're interested in is this region here from about 15 to 25 kilometers or so. M equals 0 is 0 phase lag between the maximum of the Enso event and the model result. These models are driven by sea surface temperatures, observed sea surface temperatures. M equals 3 is a 3-month phase lag, and M equals 6 is a 6-month phase lag. So the interesting thing is that WACOM shows this, this very cool anomaly by about a degree in the lower stratosphere at all longitudes about 3 months after the Enso event. But the middle atmosphere ACOM model is kind of weird in that it shows a response at all these lags, and ERA 40 doesn't show any. And in the paper, it was pointed out that the reason that there's maybe a problem with ERA 40 is that the QBO is present in ERA 40, whereas it was not present in WACOM or the middle atmosphere ACOM model. And when you do these composites, you can, I think there was not a balance between westerly and easterly shear phases when you're comparing Enso versus, or El Nino versus La Nina. Okay, so the ERA kind of gets biased by the QBO, and that's why it doesn't show there. But one of the things that this paper pointed out was that what appears to be the driving force behind this Enso variation in temperature, and remember, if you have lower temperatures in the tropical lower stratosphere, you might expect to see larger upwelling. Okay, what seemed to be driving that was the anomalies in the EP flux, primarily at mid and high latitudes. And again, there are some big differences between WACOM and the middle atmosphere ACOM model that I don't completely understand yet, and I'm hoping to talk to some folks here about it, because I want to learn more about what's driving this. But a big emphasis in this paper was these very long wavelength Rossby waves at extratropical latitudes that were associated with Enso. And then a more recent paper in 2010, Calvo et al. This is also from WACOM, and it shows anomalies in W star during Enso events. And you can see this region here where there's enhanced upwelling during Enso events. And one of the things that they concluded was that a big contribution to this enhanced upwelling was, as opposed to this higher latitude long wavelength Rossby waves propagating upward and affecting the tropical lower stratosphere by this wave driving method. They looked at subtropical gravity waves, and if you have no gravity waves in WACOM, which is kind of nice, you can turn things on and off, the amplitude goes way down of this W star anomaly, so that their conclusion was that 30 to 50% of the W star anomaly could be attributed to these parameterized gravity waves in the subtropics. Okay, so now this is the same plot I showed before with the black, but the red now is the multivariate Enso index, which is similar to kind of the index that was being used in those previous papers. but it's based on 6 observed variables in the tropical Pacific. I think it's a pretty reasonable index for Enso. And you can see this correlation seems to be pretty significant. I haven't put a phase lag in here yet. I've played around with different phase lags, and it doesn't seem to improve this linear correlation between the two. You probably wouldn't expect it to if, in fact, the optimum phase lag, according to Wacom, is about 3 months. That's kind of right at the edge of the temporal resolution that I have. So, whoops, I haven't applied it. But although one thing that is kind of interesting, I mean, it does look like there's about a 3 months phase lag there. But then when you come over here to the minimum, looks like they're right on. So it's kind of tough, and there's a lot of noise. Again, so La Niñas tend to be like 0 phase lag in this time series, whereas the El Niños, I could probably justify a 3, even here, a 6-month phase lag. One other thing, though, that's correlated that I just have to bring up, OLR. Well, obviously OLR is going to be correlated with the vertical velocity if MEI is, because Enso and OLR are correlated. Or I should say anti-correlated, right? Is that true? No, they are correlated here. That is to say that during El Nino events, you have the OLR is enhanced because I guess this is tropical average. The tropical average convection is suppressed in general compared to La Nina events. But one interesting mechanism here, and I'm almost done. In addition to these wave-type driving events, is you could imagine that clouds can affect the infrared heating by ozone in the lower stratosphere. So imagine here that if you have a positive OLR anomaly, it's associated with clear sky. The warm surface hits this ozone in the lower stratosphere, leads to infrared heating in the ozone 9.6 micron band. If, on the other hand, you've got cold cloud tops, the ozone's not seeing the warm surface. It's seeing the cold cloud top. There's less absorption at 9.6 micron, less heating. Now, there's also a shortwave effect, too. You might say, but what about the albedo effect? Yes, there's also albedo effect, and so there's increased heating from ozone shortwave UV, but that tends to get it is not as large as the infrared effect. So the net effect is there is less heating when you have high cold cloud tops. And this has been demonstrated and known for quite some time. There's a number of papers on this. Okay, so this provides perhaps another mechanism in addition to the dynamical ones, whereby El Nino, by modulating the cloudiness, could impact the vertical velocities in the lower stratosphere, independent of changes in temperature. Okay, so here's the summary. I haven't talked about CO. I didn't mention it, but CO you can get mean velocities, but the time series looks pretty crappy. So it's really not worth looking at. The variability here in the H2O vertical velocities is dominated by the QBO. Amplitude grows with increasing altitude. The annual amplitude is about half as large above 20 kilometers. As you get closer to the head, to the tape head, near the tropical Tropopause, then the annual amplitude is comparable to the QBO and is even larger. There's interannual variability associated with El Nino. And I think this is really neat because all of this emphasizes the importance of waves in the atmosphere. For the QBO, we're talking about waves in the tropics propagating upward through the easterly and westerly wind regimes, and that helps it propagate down, right? For the annual signal, we're talking about extratropical Rossby waves For Enso, there's the paper that showed the subtropical gravity waves can be really important too. So all of these things are related to wave activity. I think this is a big one too. Ongoing and continuous measurements of water vapor in the lower stratosphere are needed for monitoring variability and trends in the strength of the Brewer-Dobson circulation. But I would worry about measurements from a single site. And the nice thing about the MLS data is you get this tropical average, and that's kind of what you want for this analysis, not just a single location. And particularly now that we're kind of entering, we have this very strong El Nino, it's going to be very interesting to see what the tape recorder results are going to give us into the following year and even onward. So I think it's important to have a space-based, very high-quality measurements. One thing, though, for this tape recorder analysis is you don't really need high precision or accuracy. You just need stability over time. I mean, it's not so much the absolute value of water, but it's monitoring the signal as it goes up. And so you can really get away with perhaps not having the absolute value of the humidity right, as long as you're able to track those wet and dry signals. But here's something I want to work on, perhaps. Using hurdles data, because they have much higher resolution than MLS, factor of 2. The coverage and the duration is an issue because it only goes through, at least for this, it's a little less than 4 years. And you can this is my first cut at using hurdles data, so I know this is probably an ugly figure, but you can kind of see something propagating upward. So maybe there's a chance of using hurdles data with the higher vertical resolution, and we could shrink down the width of that Hahn window and maybe get better temporal resolution. So that's a possibility. And I wanted to thank Gabby and Frank and Ann and John Squared, which would be John Orlando and John Gilly, Bill and Sasha and Laura for making me feel welcome here. I'm going back to New Mexico at the end of the month. If you want any good green chili, let me know, and I'll bring some back. Thanks.
Okay. I've been told that you have to use a microphone if you want to ask a question. So, anybody have a question for Ken? I was wondering how you're going to make the chilies work into the discussion. Questions?
So the anomaly in the vertical motion induced by the QBO never overwhelms the overall to make it negative. It's always just weaker positive.
It's always weaker positive. That's right. I have not seen a case where there is actual downwelling in the tropical lower stratosphere.
So you compared results to Bill's paper where he was showing the shear versus the change in U for the QBO using the vertical velocities from the tape recorder, right? And you didn't seem to really get the same result he did. You got kind of what he did, but not exactly. Why do you think that is?
Yeah, I don't know. Now, the data that was in Bill's paper was the UKMO data. So the wind shear came from the UKMO analysis. The W star was calculated based on the temperatures from the UKMO analysis. I don't know whether it's something in the analysis or whether we're comparing apples to oranges.
Well, earlier in the talk, you kind of implied that the GeoCCM got the W star correct. I mean, it agreed with your tape recorder velocity. Yet when you look at, he's basically calculating an omega, it's very similar. but it doesn't seem to get the anomalous circulation from the QBO quite right. Does that make sense?
Yeah.
So in one sense, you seem to get good agreement. In another sense, you don't.
Well, there's another thing that I've I didn't point out, and maybe I don't want to put you on the spot, Bill, but the temperature anomalies are multiplied by 1.4 here, and I think that had something to do with the fact that the temperature response in the UKMO wasn't as strong as it should have been.
Could be. I think we compared it with some Singapore radiosondes or something.
And found that their temperature response was too weak. But you may have done too much of a correction. Maybe I don't know. I was just happy to get slopes that looked the same, you know. But yeah, and you know, certainly the relationship is nowhere near as compact as what I got is nowhere near as compact as this. But I guess you would kind of expect this because the model has to be internally consistent, right? I mean, they run. Yeah, I mean, they've got it. It has to obey thermal wind balance, and everything has to work. Whereas in the data, who knows what's going on? Yeah. So.
Do you see any trend in the Brewer-Dobson circulation?
Well, if you look at this, you can fit it to a line, and it does show, it does go down, okay? And you can do significance tests on that, and it's just marginally significant. But I imagine you could take a different chunk of the record, and I think it's just because of this and this at the end. So it's really premature to be looking at that. However, I think it's not premature. I guess I would say you can do it, but then you just have to interpret it with caution. That's all. Yeah, I think most of the general feeling is that this should be going up, right? That with increased greenhouse gas loading, we should see a strengthening of the Brewer-Dobson circulation.
That's what the models show.
Yeah. But another thing that can come into play here is that, remember, we're looking at plus or minus 15 north, right? And you could also have an expansion in the upwelling zone so if the overall mass stayed the same, but if that zone of upwelling increased, the mean rate of upwelling would go down. Okay, so and you wouldn't know it by looking at this because we're looking at a fixed latitude range. So I think it's kind of, it's interesting to look at, but you really have to interpret something like that with caution. And this also argues for why I think we need continuous time series of water vapor in the tropical lower stratosphere, global observations that we can use to keep an eye on this.
Right behind you, Dan, go next. Holger.
Yeah, Ken, I have a two-part question. Early on, you said that vertical mixing speeds up your vertical transport. So the true residual velocity is actually always an upper limit. Yeah? The residual vertical velocity you derive is an upper limit. I don't fully understand that one. That's part one. And part two is the averaging kernel of the MLS retrieval. That should act like a mixing term.
Yes, it should.
And so that also would mean that what you derive should be smaller, actually.
Yeah, although I believe, there's the averaging kernel on MLS, but then the way that they do their piecewise, it's a piecewise representation of the true profile. I haven't thought about the effect of the averaging kernel, to be perfectly honest with you on that. So I don't, But to answer, and maybe what we should do is we should talk about, maybe offline, about the effect of vertical mixing. Horizontal mixing is also a problem too, because there are quasi-horizontal gradients, particularly in CO, that can really mess you up, but also in water. But my argument was just that vertical mixing would tend to make these anomalies go vertical. In which case, if I tried to, I would calculate a smaller phase lag between them, and that would give me a much faster vertical velocity. Right?
Doesn't that imply, or doesn't that require that there's a gradient in the vertical mixing? A change with altitude?
I don't think so. But let's, you're here at NCAR, right? Well, I'm right down the hall, so we should talk about that. Yeah.
Next to you, Holger.
It's 3:30.
No. Actually, I have the same question with Holger. Like vertical mixing is kind of a two-way process, so it could slow down the slope, I think. Yeah, can you show the next figure like that? At the bottom of the level, no, sorry, can you show the particle profile of particle velocity?
Oh.
Yeah,
yes,
that one.
Yes.
So for the bottom lower stratosphere, like 18, I agree with you, like maybe particle mixing will kind of accelerate, but kind of time recorder. But I think the upper middle stratosphere then might slow down the signal about the motion, I guess.
Because of the gradient of the W star?
Yeah, I just assume. Yeah, but I think basically I don't think particle mixing is only one way. Like they could be two way. What do you think?
Oh, absolutely, yeah. Well, but the vertical mixing wipes out the kinds of things that, any structure that you would have here, vertical mixing, if it would tend to homogenize things, and then your anomaly would go vertical. And then,
but if you go middle of the panel, then that will homogenize like that, like.
oh.
Yeah, I'm going to let you guys talk
yeah.
about that offline. One more question here.
One of the things that sort of is physically constraining is that you'd expect the vertical velocity for the CO and the vertical velocity for the water vapor to be the same. Could you combine the two data and get a better resolution?
Oh.
And then also kind of related is the chemical reactivity of the CO presumably more reactive than the water? Would that create error in the calculation of the velocity that's not present in the water?
That is one of the things you have to worry about with CO. As you get above the tropical tropopause, then you start getting into more OH, and that's a problem. For water, the problem for water you have is that you can get oxidation of methane, which gives you water, and that can also confound the signal. But I think it's much less than for CO. For combining signals, what I'm afraid would happen is that you would probably just make things worse with the water. It's an interesting idea, though. You would have to shift so that the maxima line up. You'd have to shift the phases. But what I'm afraid of is that you would make a nice clean signal for water. You'd kind of muddy it a little bit. But I don't know.
Yeah.
Weight it, that's true. And one of the things about CO is that it's not just an annual signal, but you get these kind of pulses. And if you had good enough CO measurements, you could track so that you wouldn't be limited by the annual cycle in terms of looking at features to track. And that might give you higher temporal resolution. But you would need CO measurements with much better vertical resolution in order to do that.
I think it's easy.
Yeah.
All right. Thanks, everybody, and thanks, Ken, for a nice talk.
Oh, thank you.